Welcome to the fourth lecture of structure analysis. I think last time we have discussed about how to draw shear force and bending moment diagrams. Okay, that we have finished. This is another important topic that is going to be very helpful in structure analysis. Okay, so deflection calculation. Now the problem here is you have so many methods. Precisely, you have 6 methods to calculate your deflection for frames, for trusses, for beams. Okay, you need to have a working approach when you are going to use which method. There are 6 methods, so each method has its speciality, and your question will be very short, or you can save some time if you pick up the right method. Okay, if you pick up the right method. So what are the methods that we are having here is, we are having, first approach will be your standard approach. Okay, first one is your standard approach. Then you will have Macaulay's, I don't know the spelling, I call it Macaulay's method. Okay, then third one you are having is moment area. Okay, moment area method. There is an extension also, moment area by parts. Okay, that is included in this one. Then you have your conjugate beam method. Okay, you have conjugate beam method. After conjugate beam method, you have your energy methods. Okay, you have precisely your unit load method, and the last one is your Castigliano. Okay, Castigliano's, don't mind the spelling, I don't know, Castigliano's method. Okay, standard approach, what standard approach does is, this is absolutely a shortcut technique. Okay, to be used only in examination. Okay, I'll make you remember some standard cases, and you will use those standard cases and evaluate your deflection. Okay, Macaulay's method will be used, okay, when your standard method or shortcut is going to fail. Okay, otherwise your next choice will be absolutely be this one. Okay, so my first choice when I'm solving a question is your standard approach or Macaulay's. Okay, second choice is definitely your moment area method. Okay, conjugate beam method you will use whenever you see a hinge or moment at ends is asked in question. Moment at end. Okay, it is very important that you know this, when to use which approach, which method. Okay, so whenever you see a hinge or in the question it is asked that you calculate the moment at ends, you go for conjugate beam method. Okay, unit load you will use for trusses, you will also use it for frames. Okay, Castigliano is used for frames. Is it okay? So this is how the methods are. 6 methods you are having, and we are going to have all the methods. Okay, but you have to pick up which method you are more comfortable in, and that method you can use in exam. Okay, before we proceed any further, I want to talk a little bit about this method or this process that we usually do. It is called superimposition. You must have heard about this. Okay, superimposition means something like this. Okay, suppose you are having a beam here. Okay, it is a simply supported beam. Okay, and suppose some loading is acting on it. Some loading is acting here, this is a UDL, and another loading is acting, suppose this is your pin joint. Okay, 2 loadings are acting here. I want to get the deflection at the center, suppose del. Okay, what I do here is, I simply split this beam into 2 beams. Okay, I split this beam into 2 beams, something like this. Okay, you have pin joint and roller. What I do, I separate this UDL. Okay, and I separate this point load. Is this okay? Can I do this? Okay, of course I can do this. Okay, now what I do, I calculate deflection from here. Suppose it is del 1, I calculate deflection from here. Suppose it is del 2, then I can write, okay, I usually write like this: del is equal to del 1 plus del 2. Okay, this is the process, or this is the theory of superimposition. This is how you do superimposition. Okay, in objective sometime it is asked when it is valid. Okay, it is not always valid. You cannot always do this. You cannot split your loading into two and just add them directly. It is not always true. It is valid only under certain assumptions. Okay, first assumption is your linear behavior. Linear behavior means your stress upon strain is E, that is Hooke's law is followed. Okay, is it okay? There is no non-linear behavior in your beam. You have linear behavior. First requirement is this. Second requirement is your deflection. Okay, deflection is small. That means your delta should be small. If it is a large value, then you will have error with this method. Okay, why I am saying that deflection is small is because of P delta effect. You must have heard about P delta effect. Okay, what is P delta effect? If you remember, in RCC we learned this effect, P delta effect. Okay, if you are having suppose P loading here, okay, small eccentricity is present, so there comes a moment, okay, P. Now what happens is this buckles like this and you have a small deflection delta. Okay, because of the presence of this delta, what is happening? You will get an additional moment of P into delta, isn't it? You will get an additional moment of P into delta. Okay, so this additional moment you have to consider if your delta is large. If it is small, you can obviously ignore it. Okay, this is called as your P delta effect. Okay, and it comes when your delta becomes large. If it is small, you can obviously ignore it. Okay, these type of assumptions, it's called as 1 degree analysis. Okay, 1 degree analysis. Now you will ask me, 1 degree analysis this, so what is your 2 degree analysis? 2 degree analysis is the one where you consider P delta effect. Okay, is considered. Is it okay? P delta effect is considered. But normally wherever your superimposition is valid, there your 1 degree analysis is being considered and not the 2 degree analysis. Otherwise your superimposition principle will fail. This question is asked in objective many times. You should remember these two assumptions: linear behavior and deflection is small, then only your superimposition is valid. Is that okay? I hope you are able to understand. Moving on, let's come back to our topic. Let's start with the first method to calculate deflection. Okay, we are to calculate deflection. Okay, the first method that we are having is standard method. Standard method means by hearting. That means remembering everything. रटना बेसिकली इसको बोलते हैं. ठीक है, कुछ स्टैंडर्ड केसेस मैं तुम लोग को बोलूँगा, याद कर लो. उन स्टैंडर्ड केसेस की हेल्प से क्वेश्चन को हम सॉल्व कर सकते हैं. शॉर्टकट मेथड है. ओके, ऑब्जेक्टिव के लिए सिर्फ शॉर्टकट. ओके, शॉर्टकट ओनली फॉर ऑब्जेक्टिव. Is it okay? Okay, so you have to remember some standard cases. Okay, I will write a number of cases and you have to remember it. And don't tell me you cannot remember them. You can, because if I remember them, you can also remember them. They are pretty simple and straightforward. Okay, so they are something like this. Suppose the first one that you are having, okay, cantilever with a point load acting at the end, P. Okay, it will deflect something like this, isn't it? The dotted one, it will deflect something like this. This is your delta, and this somewhere here, this is your theta. You will have some deflection and some rotation at the free end. What is the value of deflection and rotation? Deflection is equal to PL cube upon 3EI. Okay, and theta is equal to PL square upon 2EI. L is of course the length. Is it okay? You remember this. Okay, PL cube upon 3EI is the deflection and PL square upon 2I is the rotation. Okay, second case. Okay, Again you are having, instead of this point load, you are having a moment like this. Okay, the deflected shape will look again the same way. It will look something like this, and you will have certain theta here, and you will have deflection delta here. What is the value of delta here? It is ml square upon 2ei. L is of course the length, and your theta is ml upon ei. This is what you have to remember. This is your, I think it is your second case. Okay, these are two standard cases: cantilever with point load and cantilever with concentrated moment at the free end. Okay, so you have PL cube upon 3ei as the delta, and theta is PL square upon 2ei. For the moment you have ml square upon 2ei and ml upon ei. Believe me, if you remember these, you will have great help in objective. You will have a certain edge over other people. Okay, third question you are having is something like this. Again you have your cantilever. Okay, this time instead of point load you are having UDL, something like this. Okay, obviously it is going to deflect something like this, isn't it? Here your slope will be 0 because it is fixed. You will have some theta and some delta. What is the value of this delta and theta? Your delta is equal to W L to the power 4 upon 8 ei. L is of course the length, and W kilonewton per meter is the loading. So this is your delta, and your theta is WL cube upon 6ei. Is it okay? WL cube upon 6ei. Moving to the fourth standard case, let's come to simply supported now. Simply supported, you have pin joint here and roller here. Okay, and you are having a simple P loading at the center. Okay, this is L by 2 and this is also L by 2. Okay, how will it deflect? It will deflect something like this, isn't it? Here you will have maximum deflection, say delta, and this rotation is theta. This rotation is also theta because it is symmetric, isn't it? It is acting at the center, so it is symmetric. So this is theta and this is also theta. What is the value of delta and theta? Delta is P L cube upon 48 ei. Theta is P L square upon 16 ei. Okay, P L cube upon 48 ei and P L square upon 16 ei. Okay, I think we have done 4 cases, right? So fifth case. In the fifth case, you are having your simply supported beam. You have pin joint here, roller here, and suppose now instead of a point load you are having a UDL. Okay, you are having a UDL W, length is L. Okay, how will it deflect? Like, it will deflect something like this, isn't it? Somewhere here at the center you will have maximum deflection, and you will have theta and theta. Okay, so what is the value of delta here? Is it 5 WL ki power 4 upon 384 ei? It may look very difficult, okay, to remember this, but it is very easy. Okay, if you give 2-3 tests in your test series and you revise it 2-3 times, okay, you will be able to remember it. Okay, and your rotation is WL cube upon 24 ei. Okay, these are standard cases. Later we will use superimposition and we will solve big question with these standard cases. Okay, big help in your objective. Next case is, okay, this is a very important one, many times asked in objective. Suppose you have simply supported beam here, and for loading you are having a moment m0 at the end. Okay, moment m0 at the end, it deflects something like this. Okay, slightly tilted towards the where your moment is acting. Okay, so here somewhere here you will get your maximum delta. Okay, here you will get your maximum delta. The rotation is very important. Okay, if you don't remember delta, it is fine, but you have to remember the rotations delta 1 and delta 2, or theta 1 and theta 2. Delta is equal to how much? I don't expect you to remember this, okay? M naught L square upon 9 root 3 EI. Okay, don't have to remember this, no need. Okay, the important thing that you have to remember is theta 1 and theta 2. Okay, theta 1 is M naught L upon 3 EI, and theta 2 is M naught L upon 6 EI. Okay, this is important, this is what we are going to use. Delta is irrelevant. Okay, delta is irrelevant. If you want to remember, you can remember it occurs at L by root 3 from one end. Okay, this is not important, no need to remember this very difficult figure to remember, M naught L square by 9 root 3 EI, but you should remember theta, both theta you should remember. This one is obviously bigger because M naught is acting here, so it is M naught L upon 3 EI. This one is smaller, so it is M naught L upon 6 EI. Okay, I think we have 6 cases till now. Okay. Alright. Fixed cases. Fixed cases, I think this is your 7th one, right? So you will have fixed case. Fixed means this is also fixed, this is also fixed. Okay, and then 8th case we can have something like this. This is fixed, this is again fixed. Here you will have one point load P, and here you will have UDL. Okay, W. Obviously it's going to deflect something like this. Okay, here also it will deflect the similar way. Okay, here slope is 0, of course. Okay, this is your delta, this is again your delta, no need for theta. Okay, theta is obviously 0 here also it is fixed, isn't it? Now the delta for this case is equal to delta for simply supported by 4. Okay, this is how I remember it. This is very simple way to remember it. Okay, delta SS is nothing but if you have the same beam, okay, if you have the same beam and you have simply supported case, okay, P, so this thing here is your delta SS. Okay, delta SS, and this we have already covered. How much is this? It is P L cube by 48 EI, isn't it? 1/4 of that will come in fixed support. Okay, 1/4 of that will come in fixed support. For this case, your delta is delta simply supported by 5. 1/5 of simply supported case, you will have deflection. Okay. Moving on, I think we have done 8 cases, right? There are total 10 cases that you have to remember. Okay. Okay. Ninth, right? Ninth case. You have simply supported case again, and you have the same fixed case. Okay. You have simply supported here, and you have fixed here. Okay. And your P, rather than acting at the center, it is acting at A from here and B from here. Same is the case here also, A and B. Okay. Here it will deflect something like this. Okay. Here it will deflect something like this. Okay. So in this case, we are concerned about delta, that is delta under the load. Okay. Sometimes in objective what he asks, is this delta the maximum? This delta. Okay. Answer is not necessarily. Okay. It may so happen that your maximum delta occurs somewhere here. It is possible. It is not necessary in this case or in this case that your delta occurs maximum under the load. Okay. So this delta is given by P A square B square upon 3 EI L. Okay. And here the delta, this delta under the load is given by P A cube B cube upon 3 EI L square. Is it okay? P A square B square by 3 EI L, P A cube B cube by 3 EI L square. This is your 10th case. Moving to the 11th case. Okay. Okay. Just the last 2 cases. Okay. There are many cases, but this is what you can remember actually, and it will be helpful in objective. Suppose you have propped cantilever and you have moment here m0. Okay, of course you can evaluate these things with your standard methods. I will tell you how you can evaluate this, but it is time consuming. From objective point of view, you have to be quick, so you need to remember these. Okay, this theta is very important. This is theta, and somewhere here you will get delta. So your delta is ml square upon 27 ei, ml square upon 27 ei, and it take place at 2l by 3 distance from here. This theta here is, this is important, m naught l upon 4 ei. Okay, this is very important, m naught l upon 4 ei. Okay, last case you are having a cantilever with triangular loading. Triangular loading means, okay, something like this. Suppose W here and length is L, it will deflect something like this. You will have delta here and theta here. Okay, so your delta is equal to WL to the power 4, WL की power 4 upon 30 ei, and your theta is WL cube upon 24 ei, 30 and 24. Is this okay? These are the 12 cases that you should remember. Let's revisit them once again, okay, so that you are able to remember something. Okay, this is very simple. If you have a cantilever and a point load is acting at the free end, your deflection will be PL cube upon 3 ei and rotation will be PL square upon 2 ei. Okay, PL cube by 3 ei and PL square upon 2 ei. If you have moment, it is ML square upon 2 ei and ML upon ei. Okay, two cases. Third case, you are having W here, so you will have WL to the power 4 8 ei, okay, is your deflection, and WL cube upon 6 ei is your rotation. For this one, it is PL cube by 48 ei or PL square upon 16 ei. Okay, for W you have 5WL to the power 4 upon 384 ei, okay, and you have WL cube by 24 ei. If you have a moment like this, I have told you deflection is not necessary that you should remember the deflection, just you should remember the theta angles. This is ML upon 3 ei and this is ML upon 6 ei. Okay, only these two you should remember. No need to remember this deflection or the location. Okay, for this type of case you can relate it to simply supported case. This is 1/4 of simply supported case, the deflection, and here deflection is 1/5 of your simply supported case. Is it okay? 1/4 and 1/5. Here you are having P load here. This is your delta. It will come out to be P A square B square upon 3 ei L, and if it is fixed, it will come out to be P A cube B cube upon 3 ei L square. Okay. In this case, the only important thing is this theta. Okay, this you should remember absolutely. M naught L upon 4 ei. Okay, it is a propped cantilever. Propped cantilever. Okay, so you should absolutely remember this M naught L upon 4 ei. Here you should remember both the values because this will come in very handy. Okay, so the values are WL to the power 4 upon 30 ei and 24 ei. Okay, you can remember these numbers 30 and 24. Rest is the same. Okay, in all the cases. So I think that is it. These are the cases that you should know. Okay, now we can solve some questions. Okay, let's start with something simple. Okay, suppose this is your question 1. Okay, you have to use standard method only. Use standard method only. Okay, whatever formulas you have remembered till now, use them only. And this is your first question. Say A, you have your cantilever, simple cantilever. Okay, okay, and a point load P is acting here. Okay, I want to calculate the deflection at C. Delta C is equal to question mark. This is your question. Okay, now you will tell me sir, I only remember this value. Okay, delta is equal to PL cube by 3EI. I want deflection at C, that is I want this value, delta C. Is it okay? I want this value, not this value. Okay, how will you evaluate it? Okay, there is a very simple procedure called the shifting procedure. Okay, shifting procedure. Wherever you want to calculate your deflection, at that point you shift this load. Okay, like this. Suppose you have fixed here, you shift your loading P at point C. Okay, now you cannot just shift this load from here to here. Okay, because you will have to counter the moment also. At C you will get some moment also. That moment will be equal to how much? Suppose this distance is say x. Is it okay? Suppose the distance is x, so this is obviously L minus x. So what is the moment that will be applied at C? Is it P into x? Okay, is it P into x? So can I do this? Okay, are these two equivalent? Of course they are. They are equivalent. Okay, you can obviously do this. You can shift this loading to C. Okay, and you can apply a moment. Now this has actually is converted into our standard case. अभी हमारे standard case में convert हो गया है. अब अगर तुम deflection निकालोगे, okay, so this length is L minus x, right? So what is the deflection due to this P? अब तुम superimposition principle use करो, इसको further दो beam में तोड़ लो. Okay, you have one P load here plus, okay, another cantilever and a moment Px here. Okay, this distance is L minus x, this distance is L minus x. Okay, अब यहाँ से जो deflection है उसको del 1 बोल लो, यहाँ से जो है उसको del 2 बोल लो, और del c तुम्हारा कितना हो जाएगा? del 1 plus del 2. Superimposition principle. Okay, do you know what is the del 1 here? It will deflect like this. What is the value del 1 here? It is PL cube upon 3EI. But be careful, what is L here? L is not L, it is L minus x. Okay, okay, so what is the value of L here? Suppose I am calculating del 1. Okay, del 1, this del 1 I am calculating. Okay, so your del 1 is equal to, you already know it is PL cube upon 3EI. P is the same, your L is now L minus x cube upon 3EI. Is it del 1? Okay, come to del 2. What is the value of del 2? Here you will have some deflection. This is your del 2. You already know for constant moment the value is ml square upon 2EI, isn't it? What is your moment? Is it px? What is your L? Is it L minus x divided by 2EI? Okay, okay, so your delta C, deflection at C, is coming out to be P L minus x cube upon 3EI plus Px L minus x square upon 2EI. So simple, isn't it? Now you will use many methods for this, moment area and whatnot, but this is the simplest method that you can do and evaluate this type of question. Let's have another question. Okay, second question, say same question, you again have the same cantilever. I'm just showing you how to use those formulas. Suppose you have loading here, okay, and you want to calculate deflection at A, or say rotation at A also. Deflection and rotation both I want. Can you calculate rotation in the previous case? Of course you can. You can say if rotation here is theta 1 and this is theta 2. Theta 1 is how much? It is P L square upon 2EI, I think. Okay, P L is L minus x square divided by 2EI, and theta 2 is how much? ML upon EI. M is Px, L is L minus x upon 2EI. You sum them up, this is your total rotation at C. Okay, now you come to this question. P is applied here. Okay, this is your cantilever. Okay, this is your cantilever. You want to calculate delta A and theta A. Okay, delta A and theta A is what you want to calculate. It will deflect something like this. Okay, is it okay? Let me tell you one data, that up to this loading, okay, up to this loading, the curve is going to be parabolic. After the loading, there is no loading on the span, so it will remain straight. Okay, so what I'm saying here is this much curve will be parabolic, okay, and this much curve will remain straight. Is it okay? Okay, now how will we use this information? I know the deflection here and the theta here, isn't it? Can I use that theta to get the deflection at A? Okay, of course I can. See, first you give me this delta and theta here. Okay, what is the value of delta and theta? Delta, suppose I am naming this point B, so delta at B is P, suppose this is A, okay, so this will be L minus A. So P A cube upon 3EI is your delta B, and what is your theta B? Theta B is nothing but PA square upon 2EI. Is it okay? This is at B point. I want deflection at A point. Now closely look at this curve. Okay, we can use this data, parabolic and straight. It is something like this. It is parabolic up to here. Okay, I don't know how to draw parabola like this. It is parabola and then it is straight. Okay, here you know this theta. Okay, if you extend this line, you know this theta also. Okay, I think it is called, what is it called, corresponding angles or alternate angles, whatever. Okay, you know this length. Okay, you know this length, this is your original level. Okay, you know this length, you know this theta is delta B. Okay, can you get this value from triangle? If you know this length, it is L minus A. If you apply tan theta here, okay, this length will be theta times of L minus A. Okay, and this entirely is your delta A. I hope you are able to understand. Simple triangle I am using. Okay, look here. What I am doing here is this, you know, this is delta A. This value here, okay, this value is theta. So you apply tan theta here. This distance you know, so you will get this distance. Is it okay? So your delta at A is given by delta at B plus theta times of L minus A. Theta at what? Theta at B again. Okay. So you can just put the values here. Theta at B is nothing but PA cube upon 3EI plus theta at B is nothing PA square upon 2EI into L minus A. This is your deflection at A. Okay. I hope you are able to understand this. Moving to the third question that we are having. These type of questions are very much asked. Okay. Suppose you are having something like this. Okay. Suppose you are having something like this, and this is your fix. Okay. Load is acting, P load is acting here. Okay. P load is acting here. Inertia of this section is 2I and inertia of this section is I. I want you to calculate the deflection at point C. Deflection at point C. Okay. Now there is a slight trickiness. Okay. You have to do the exact thing, exactly the same thing that you do in the previous question. Previous question means the first question. Okay. Do the same thing that we did in the first question. This thing, shifting procedure. Okay, just shift the P load to the point where you want to calculate the deflection and apply a resulting force and a moment. Okay, same thing we will do in this question also. Okay, same thing we will do in this question also. What you do here is you make the same beam. Okay, same beam, something like this. Okay, you apply P load here and a moment equal to, suppose this is your A, okay, this is your B, and overall length is L. Okay, so no need to say that L is equal to A by B. So this is PB. Is it okay? Can I do this? Of course I can do this. Okay, this is your 2I and this is your I, and at this section it is called C. Now can you solve it? Now it is very, very easy, but be careful about inertia. This is 2I and this is I. Okay. Now delta at C I want to calculate. What is delta at C? Is it P, L is A, P, this is A, right? and this is b. So PA cube upon 3, careful, I is not I, it is 2I, okay, 2EI. So it will be PA cube upon 6EI. Is it fine? Delta at C. What is theta at C? Is this delta at C, or it has one more component from this moment? What is the moment? Okay, I made a mistake here. Delta you will get from two things, right? Delta you will get from this point load also and this moment also. Okay, so delta from point load and delta from moment. Okay, what is delta from point load? Just now we have wrote it is PA cube upon 3EI. Okay, what is delta from this moment? Is it ml square upon 2EI? And I is obviously what? Okay, I am also making mistake here. I is nothing but it is 2I. Okay, moment ml square upon 2EI, m is PB, okay, L is A upon 2E, I is again 2I. Okay, this is your delta at C. Okay, see how quickly we are able to solve. Okay, if you use any method, moment area or whatever, you require a lot of time, at least 5-10 minutes it will take, but this method is quick. Delta C is nothing but delta that is coming due to theta that is coming due to point load and theta that is coming due to moment. What is the theta due to this point load? Is it PA square upon 2EI? PA square upon 2E 2I plus what is theta due to this moment PB? Is it ml upon EI? M that is PB, L that is A upon E and I that is 2I. This is your theta at C. Okay, theta at C. Suppose in the same question, just now that question that we have solved, okay, in the same question, suppose your load is applying at the same place and I want to get theta and delta at this point B. I want theta at B and delta at B. Okay, can you solve it? Okay, it is simple. What you do here is you follow the same procedure. Just previously what you have done, you follow the same procedure. Okay, for this you may have to change your approach. Okay, now there is a problem in this beam. Your I is varying throughout the section, so I cannot write here PL cube upon 3EI directly. Okay, delta B I cannot write this value, okay, because your I is varying throughout the section. Okay, I have a special approach for this thing. Okay, what you can do here is, suppose that this point C, as we called earlier, is fixed. This is fixed. Okay, this point C is fixed. Suppose, now can you tell me what is your delta B? Of course you can. Okay, it is nothing but PB cube upon 3EI. Okay, and your theta is PB square upon 2EI, isn't it? But is this the answer? No, it is not the answer, because your C point is not fixed. Your C point is having some deflection and some rotation. So what you have to do, your actual, let me call this theta B prime and delta B prime. So your actual theta B will be equal to delta B prime plus delta C, and your theta B will be equal to theta B prime plus theta B, theta C. Okay. Earlier you have calculated these values, theta C and delta C. Put those values. Theta B prime you know, theta delta B prime also you know, so you can get the value of B. Okay, so this type of shortcuts you can use. Okay, this is a very simple approach, very handy approach also. Okay, otherwise you have to draw the moment diagram and all, and you can solve. Okay, but this is a very simple approach. Okay, just assume that your C is fixed. Okay, and then you have already calculated the value for C, so you can get the value for deflection at B. I hope you are able to understand this. Okay, let's solve one more question. Okay, one more question, very much asked in your objectives. It is something like this. again you have your cantilever, okay, and this type of loading is acting just the way up to half. Okay, this is your A length, this is your B length, overall length is L. Okay, find the deflection at point C, that is here, and B also. Suppose find deflection at C and deflection at B. How will you find? Okay, you obviously know it will deflect something like this up to C, it will be parabolic. After that it will be a straight line, isn't it? After that it's going to be a straight line. So this part from here to here is a straight line, okay, otherwise this part is a parabola. Okay, we will use this data. Now can you give me the value of deflection at C? Obviously this is our standard case, isn't it? What is the value from our standard case? What is the value from our standard case? Is it WL to the power 4 upon ATI? Isn't it? WL to the power 4 upon ATI. Is it WA to the power 4 upon ATI? What is theta C? Is it WA cube upon 6EI? Okay. So you know these values. You know the delta here. Okay. You know this delta C, and you know this angle theta C. Okay. If you see, these are opposite angles, so this is also theta C, isn't it? This is also theta C. Okay, this is delta C. You can get this value from tan theta. It will be B times of theta C. Okay, so your theta at this point, let me name this point say B. Okay, so theta at B is equal to delta at C plus B times of theta C. You know the value of delta C, you know the value of theta C. Put the values here, you will get the value of delta B. Is it okay? I hope you are able to understand this. Moving to a few more questions. Again, suppose you have a cantilever. Rather than having loading here, suppose you had loading in the other half. Okay, let this be A and this distance be B. Okay, now can you tell me the deflection? Okay, this is not my standard case. In my standard case, my loading should start from here, but it is starting from here. Okay, so this is not my standard case, but if I use my brain slightly, I can convert it into my standard case. Okay, how can I convert it into my standard case? What will I do? I will continue loading up to this point W. Is it okay? Now what will I do? I don't have loading from say here to here. Okay, for this B distance I am not having any loading, so for B distance I will apply opposite loading. Can I do this? Can I draw this beam like this? Okay, this is your A distance. Is it okay? Of course I can. And this case just now we have solved, just now previous we have solved. Okay, so we can superimpose these two cases and solve for this beam. Is it okay? Okay, so further you can split this into two questions. You can have simply a UDL like this, plus you can have opposite UDL like this. Okay, and you know the answer to this case, you know the answer to this case, just now previously we have solved, so you can add the deflections from both and get the answer for this beam. So this is how you have to use your brain, okay, to get this, use these standard formulas. They are very handy in objectives. Okay, you can solve objectives very quickly. Similar to this, I want to show you one more question where you can actually use your brain. Okay, suppose you have cantilever like this and you have loading like this. Is this my standard case? No, it's not. My standard case is this. Okay, in my standard case, don't get confused, my loading is like this, not like this, what I have shown. Okay, this is my loading, not like this. Can I convert my standard case, this case, into this case? I can. Okay, how? If you apply, okay, if you apply your mind slightly, you can draw another cantilever, and what you do, you use UDL here in the opposite direction. Is it okay? UDL here in the opposite direction you can use. okay, or rather what you do, not in the opposite direction, you use UDL in the downward direction here, okay, and here you can use in the upward direction, okay, here you can use it in the upward direction. Now suppose I want to calculate deflection and rotation at point C, okay, so this is my case 1, this is my case 2, so my delta at C will be delta from case 1 plus delta from case 2. Is it okay? Do you know the deflection from this case? What is the deflection from this case? Is it WL to the power 4 upon 30 EI? This is WL to the power 4 upon 30 EI. The direction is upward, okay, upward I am taking as negative because this will produce deflection like this and this will produce deflection like this. So your deflection del 1 is upward where del 2 is downwards, so I have to subtract them. Plus del 2 you already know, it is W L to the power 4 upon 8 EI. So this is your net del C. Is this okay? What about theta? Theta C is again theta 1 plus theta 2. Theta 1 value you already know, it is WL cube upon 24 EI, okay. Now what is the direction of this rotation? If you see here, it is anti-clockwise, okay, and if you see here, this is clockwise, so you have to again subtract. Suppose anti-clockwise I am taking as positive and clockwise I am taking as negative, so it is minus theta 2 is how much? Theta 2 is nothing but WL cube upon 6 EI, okay. So be very careful with the direction. See here, this theta is like this, clockwise, theta 2, and this theta here, this theta, it is anti-clockwise, theta 1. So I have to subtract them, I cannot add them, they are in the opposite directions. I hope you are able to understand. Okay, you can have a few more questions if you like. Okay, one question. Alright, something like this. This is very interesting question, okay. You have pin joint here, you have a roller here, okay, and this length is A, this length is I, where P is acting here, okay. You have to find me deflection at this point, C. Can you do it by simply using your standard results? Yes, you can. Okay, yes, you can. Think about it. First, what you do, you forget that this is a roller support. Rather than a roller support, you assume that this is fixed. If this is fixed, your beam will deflect like this, and you know the value of this delta. Say I'm calling it delta 1. This is PA cube upon 3A. Okay, but in reality, this is not a fixed joint. It is actually a roller. Okay, it is actually a roller. So what I will do here is, I will shift this load P, okay, I will simply shift this load P like this. You have roller here, I will shift this load P here, and also I have to apply a moment also, P into A, okay, so I will apply a moment P into A. This P will have no effect because it is directly acting on your roller support, okay, so you will have no effect of this vertical force P, just this moment is going to give you something like this. Okay, here you have no loading, so this will be straight line. Can you know, give me this angle theta? Can you give me this angle theta? Yes, we have already done this case. It is nothing but equal to ml upon 3ei. So m is PA, L is L upon 3ei. Is this okay? ml upon 3ei. This value is A. So can you give me this deflection? Delta 2 say. Delta 2 is nothing but A into theta. A theta is PAL upon 3ei from here. Okay, PAL upon 3ei. So you know the value of delta 2. Okay, your delta is nothing, delta C is nothing but delta 1 plus delta 2. Once you have fixed the support, you got this, then you release the fixer, so you have to apply a moment here, then you got the deflection. So the sum of these two deflections will be your delta C. So it is PA cube upon 3ei plus PA square L upon 3ei. Is this okay? I hope you are able to understand this. Okay. One more question I want to solve. It was asked in GATE, I think, last year or last year. It was something like this. I don't remember it exactly, but I think it was something like this. You have this type of beam here, okay? It was pin joint here, roller here, say pin joint here, okay? And you had a moment M here, okay? Obviously it's going to deflect something like this, okay? It's going to deflect something like this. The value of theta was asked, okay? Value of this theta was asked. Now the way you can solve this is, the way I solved it is, this is your, say, same beam. What you can do, you can split this beam into two, one beam and one beam, okay? Now what you can do, you can assume pin joint here, roller here, and pin joint here, and you can distribute m by 2 and m by 2. This type of thing also you can do, okay? With this m by 2, can you calculate the value of theta? Of course you can. This is nothing but ml. Suppose this is L and this is also L. So this is ml upon 3ei. So it is m by 2 L upon 3ei. What is this value? It is m by 2 L upon 6ei. Okay. This was asked in paper. This is a simple approach to solve this type of problem. Obviously there are many other approaches, but this seems to be the simplest one. Okay. So you can do this type of thing also. So I think we are done with our first type of method, that is our standard method. Specifically this will be used only for objectives, okay? But you should remember all the standard cases. If you remember the standard cases, it will be a huge help for you in exam, okay? I think in the next class we will start with Macaulay's method. Thank you.